Welcome back. Design junkies to mechanical engineering made simple. Today, we are strapping in for a deep dive into something utterly fundamental to our modern world: combustion. When most people think of an engine, they just think of a simple bang, a bit of fuel, a bit of air, and then a flash of heat. But if you're trying to engineer a cleaner, more efficient future, you realize pretty quickly it's anything but simple. We have a dense stack of sources here covering thermodynamics, chemical kinetics, and the messy reality of energy conversion.
Our mission today is, well, it's pretty straightforward. We want to move you past that high school chemistry equation. We need to define the hidden complexities that engineers grapple with, like the molecular dynamics that determine not just how much power you get, but how many toxic pollutants you create. We're going to show you why the quality of the energy released is often more important than the total quantity.
And that's the core tension, right? Because when you look closely at what's actually happening inside that combustion chamber, it is not a simple, clean burn. It's a high-speed, high-temperature, utterly chaotic molecular barn dance.
Okay, let's unpack this and start with the dancers themselves. We start with the simplest concept. You put reactants in,
Fuel and air?
and you get products out, usually carbon dioxide and water. On paper, it looks like a one-way street, a total conversion.
And that's exactly where the first complexity arises. In real life, especially at the incredibly high temperatures you find in an engine, combustion is, well, it's inherently statistical. Yes, atoms and molecules combine to make products, but those product molecules, the CO2 or the H2O, they can also break down again.
Wait, so the end products are actually dissolving back into the ingredients?
They are. This molecular breakdown process is called dissociation. Think of it as a dynamic equilibrium. The whole mixture is taking part in this molecular barn dance, and the absolute tempo, the pace of that whole system, is controlled entirely by the temperature.
So the hotter it gets, the more chaotic the dance. Exactly. The hotter the reaction gets, the more aggressively the products try to dissociate.
That's fascinating. But if we're talking about real engines, we are dealing with milliseconds, so the speed of this reaction must be astronomical.
It is, but what simplified models always overlook is that the actual rate at which these reactions occur is finite.
It's not instantaneous.
It's not instantaneous. And this finite reaction rate is absolutely critical because it is the fundamental cause of some major pollutants, specifically the oxides of nitrogen, or NOx, which we'll dive into later.
So we have the chemistry dictating the speed of the reaction, which is thermodynamics, but the sources make it clear that the physical reality of the chamber is just as important. We also have to consider the rate at which the fuel and air can physically mix before they can even react.
Precisely. Fluid mechanics controls the mixing rate, how quickly fuel molecules can find oxygen molecules. Thermodynamics controls the chemical reaction rate, how quickly they actually decide to bind once they meet. Both must be maximized for peak performance.
And when we talk about the fuel itself, we're usually talking about hydrocarbon fuels. We might think of pure methane, CH4, or octane, C8H18, but in practice, they're almost always a complex blend.
Right, and central to controlling the dynamics is stoichiometry, which is basically the art of getting the air-fuel mixture exactly right. We quantify this using the equivalence ratio, phi.
For the listener, what does that number tell us?
If phi is less than 1, you have a weak or lean mixture, meaning there's excess air. This is generally preferred for efficiency and low emissions. If phi is greater than 1, you have a rich mixture, meaning there's excess fuel.
And it's that rich mixture that causes immediate engineering problems we can't accept today. If you have too much fuel and not enough oxygen, what exactly goes wrong?
You get incomplete combustion. The available oxygen, the O2, will preferentially combine with the hydrogen in the fuel to form water. This leaves the carbon atoms without enough oxygen to fully convert to CO2. Instead, you get the partial oxidation of carbon, which produces extremely toxic carbon monoxide, or CO.
So running rich is just, it's off the table.
For most systems, yes.
Yeah.
It forces engineers toward very precise lean burn control. So we've established how fast this dynamic reaction is. Now let's rewind and talk about what exactly is reacting and where all that stored power even comes from. Here's where it gets really interesting. It's all stored in the chemical bonds.
So if I understand correctly, the energy contained in the molecule is fundamentally linked to the concept of bond energy, the energy required to break a molecule into individual atoms. Is that essentially the potential energy stored in the molecular glue?
That's a great way to put it. When you form a molecule, you release energy. To break it apart, you must put energy back in. That concept is the bedrock for calculating fundamental molecular properties, like the enthalpy of formation, often written as delta H subscript F.
But the sources warn this isn't always simple addition. Complex structures throw curveballs.
They absolutely do. Take benzene, for example, which has a ring structure. Its stability and energy content are higher than you would calculate by simply adding up the single and double bond energies.
Why is that?
Because of resonance. Resonance means the electrons aren't sitting on fixed seats between specific atoms. They are delocalized. They're moving across the entire molecule. Imagine the energy isn't stored in one locker, but spread out across an entire safe deposit box network. This delocalization stabilizes the structure and allows it to store substantially more potential energy.
So structure is key.
Structure matters immensely to how much punch the fuel packs.
And while the big payoff reactions, the ones we want, like converting carbon monoxide and oxygen into carbon dioxide, are exothermic, meaning they release energy.
We must remember dissociation reactions. We noted earlier that the formation of nitric oxide, NO, which happens at high temperatures, is actually endothermic. It requires an energy input.
So the pollutant is actually stealing heat from the reaction.
It is. The very act of creating a key pollutant is drawing heat out of the system, further depressing the peak temperature.
This leads us naturally to how engineers practically measure the total energy release, the calorific values or heating values. We have the lower and the higher.
The lower calorific value, or LCV, is what engineers almost universally use in engine and turbine calculations. It assumes that the water, the H2O, produced during combustion, remains in the vapor phase a gas.
And the higher value.
The higher calorific value, or HCV, is higher because it assumes that water product is condensed to liquid, releasing the latent heat of vaporization as extra energy.
So LCV is preferred because in a hot engine exhaust, the water almost always remains a gas.
Exactly. If you calculated engine efficiency based on the HCV, you'd be counting energy release, that latent heat of condensation, that the engine simply cannot capture because it exhausts that water as vapor. It's a pragmatic choice based on the reality of the process.
That makes perfect sense. Okay, now we move from calculating static energy content to the dynamic reality inside the combustion chamber. We need to talk about chemical equilibrium, which is all about what the mixture wants to do over infinite time, which is minimize the Gibbs energy, G, of the total system.
Minimizing that Gibbs energy is the thermodynamic driving force for dissociation. We established that dissociation limits the peak temperature, but let's put a number on it. This effect can easily cost you 10 to 15% of the theoretical maximum power output in a high-performance system. Dissociation is the fundamental reason why real-world engines never reach the theoretical peak temperature and pressure.
So equilibrium defines the potential state of the mixture, and the concentration of those end products in equilibrium is calculated using the law of mass action. But that assumes infinite time, and we know our engines operate in fractions of a second.
This is the critical transition from theory to practice. Because time is finite, reactions are governed by chemical kinetics, or reaction rates. Kinetics is the study of how fast those reactions actually proceed.
And I remember from the sources that reaction rates are ridiculously sensitive to temperature.
They are. The dependence is governed by the Arrhenius equation, which incorporates the activation energy, E, required for the molecules to get over that hump and react. The key takeaway is, small increases in temperature lead to huge exponential increases in reaction speed.
And this kinetic limitation is the primary driver behind the most insidious pollutant. Thermal NO, or nitric oxide.
Thermal NO is formed by the combination of nitrogen and oxygen from the air itself. The reaction only becomes fast enough to happen at extremely high temperatures, peak temperature. It requires such high energy that the reaction rate is relatively slow, even at 2000 Kelvin.
So what happens in the engine?
As the gases reach peak temperature and pressure, NO starts rapidly forming. But the moment the piston moves and the gases expand and cool, that formation rate crashes to almost zero. Because the time spent at high temperature is so brief, the NO doesn't have time to reach its low temperature equilibrium state, which would be near zero concentration.
So it's trapped.
Instead, the high concentration of NO created at the peak is essentially frozen into the final exhaust products.
That's a perfect example of kinetics trumping equilibrium. It's like a factory trying to make perfect cars. Equilibrium says they should make perfect cars, but kinetics says they only have 30 seconds, so sometimes they rush and leave a loose bolt, and that loose bolt is the NO.
That's a spot-on analogy. We also have carbon monoxide, CO. While we know rich mixtures are the main culprit, even in perfectly lean mixtures, CO exists due to that CO2 dissociation we discussed earlier.
And finally, particulates, or soot. Where do they fit into the dynamics?
Particulates are generated mainly by combustion systems that rely on diffusion burning, think large diesel engines or gas turbines. In these systems, the fuel and air don't mix perfectly before combustion. Instead, localized rich zones are temporarily created, producing solid carbon particles before they can be oxidized later on. The amount of soot is also strongly affected by the fuel's sulfur content, which acts as a precursor to particle formation.
Okay, we've handled the chemistry, the thermodynamics, and the kinetics of the reaction. Let's shift our focus to the ultimate payoff, the quality of the energy itself. The first law of thermodynamics simply tells us that energy is conserved. You get out what you put in.
But the second law is the harsh reality check. It limits how much of that conserved energy can actually be converted into useful work. This is the difference between energy quantity and energy quality.
This brings us to the formal definitions of maximum available work. For a closed system, we look at the Helmholtz energy, F, which is calculated as U minus Ts.
And for open-flowing systems, which is what most power generation involves, we focus on the Gibbs energy, G, calculated as H minus Ts. This represents the maximum useful work obtainable at constant pressure and temperature.
In both of those equations, that Ts term temperature multiplied by entropy is the villain, isn't it?
It is the key constraint. The Ts term is the unavailable energy. It's the portion of the energy that, thanks to the second law, must be thrown away because of inherent inefficiencies in any real process.
And since all real processes, from friction to heat transferred to the combustion itself, are irreversible, they inevitably degrade the quality of the energy. The maximum useful work available from the products is always less than the potential available from the reactants. We lose availability in the process.
And this reality is what makes the fuel cell such a powerful, revolutionary concept. Traditional engines are heat engines. They rely on combustion to raise temperature, and they are thus constrained by the Carnot efficiency, which is a hard second law limit.
But fuel cells operate differently.
They do. They convert the Gibbs energy of the fuel directly to electricity, which is a form of work, through an electrochemical reaction. Crucially, they are not heat engines, which means they are not constrained by the relatively low Carnot efficiency limit. They sidestep the thermodynamic irreversibility inherent in converting chemical energy first to heat and then attempting to convert that heat to work.
That distinction really crystallizes the difference in heating values we discussed earlier. We use LCV for engines because the water stays vapor. But the sources show that fuel cells often target the HCV, the higher calorific value, because they operate isothermally and are structured to release the full enthalpy, resulting in liquid water as a product.
They capture that latent heat because they are converting chemical potential directly to electrical potential. They represent a pathway to greatly minimizing the entropic losses that plague every heat engine built on Earth.
So let's quickly consolidate the key knowledge nuggets we've extracted for you.
We established that combustion is a statistical molecular barn dance, where high temperatures drive dissociation, which costs you efficiency and limits peak output. We learned that the energy comes from the breaking of chemical bonds, which we quantify using LCV for engines, because the water is exhausted as vapor.
And critically, we realized that in the real world, the production of harmful pollutants like NO is a race governed by finite reaction rates kinetics, leading to the phenomenon of high NO concentrations being frozen into the products.
Understanding these limits, from the complex geometry of a hydrocarbon molecule to the ultimate constraints set by Gibbs energy, is essential for engineering innovation, driving the search for cleaner, more efficient energy conversion.
And that leads us to a final thought for you to consider about energy quality. We know that every real process degrades the quality of energy in the universe because it creates irreversibility. When we look at the rise of the zero emissions vehicle, or ZEV, we often celebrate the local lack of pollution, but the energy still has to come from somewhere.
Which often just shifts the pollution source elsewhere, from your city to a power plant far away.
Exactly.
The real engineering challenge moving forward isn't just conserving energy quantity, the first law. It's about fundamentally finding new mechanisms, like fuel cells, that focus on conserving the quality of energy, reducing the entropic degradation of our most valuable resources. That's the frontier of energy science.